In this lecture, we're going to look at buoyancy and stability. So buoyancy is really just a special case in fluid statics where we're looking at the net force in the vertical direction of a fluid acting on a body, submerged or partially submerged in a fluid. So buoyancy force is the net force due to hydrostatic fluid pressure acting on an object. So consider any submerged object. So I'm showing here an arbitrarily shaped object submerged in a fluid. Now this object just happens to be fully submerged in the fluid. We'll talk later that it could be partially submerged, so it could be floating, so only part of it is submerged, and everything we're going to say here will still be the same. So this is a free surface. Remember what this symbol means? Means that's a free surface, so we have atmospheric pressure out here, and as we go deeper and deeper into this fluid, of course, the pressure is going to increase. I have a coordinate system set up here. The only coordinate we need in this problem is a vertical coordinate, so I'm going to point Z straight up. So Z equals 0 at the surface and Z pointing upwards. So we're interested in the net force on this thing due to fluid pressure. Well, we could go back to our expression for force on a surface and use that, but realize to apply it, we need to know the shape of this surface. We need to know the orientation of this surface. Well, we can do a simplified version of that to figure out what the buoyancy force is. Now, in order to do that, what we're going to do is take a vertical slice of this body. So this dark black slice here is a portion of this submerged object. Now that slice is going to have some volume, which I've called dV, and it's going to have some cross-sectional area at the top called dA, and the area at the bottom is going to be the same. So dA is that little patch of area, and dV is the volume of this vertical slice. So in order to calculate the net force on this object, we're going to calculate the net force on this slice and then add up all of the slices or integrate over the entire volume of the object. Well, in order to calculate the net force on this slice, we're interested in what is the pressure at this end and what is the pressure at this end. Because fluid is going to be pushing downwards on the top of this slice, and it's going to be pushing upwards on the bottom of this slice. So in order to figure those forces out, we need to know the depth of the fluid at those 2 points. So moving up and down in this fluid, we're moving in the Z direction. So the top of this slice will have some Z coordinate, which I'm going to call Z1 temporarily, and the bottom of this slice will have some other Z coordinate, which I'm going to call Z2. Realize that because I have Z equals 0 here, positive Z pointing up, the actual numbers for these will always be negative because everything in the fluid here is in the negative Z direction, but that doesn't matter. These are just variables that represent the top and the bottom of this slice. So we're first going to calculate the net force in the Z direction on just this slice, and we'll call that dFz. Now notice we're not calculating all 3 components of the force here. We're only calculating the vertical component, so the component in the Z direction. So we're going to denote this force as dFz. Notice no vector here, but instead we have a subscript Z to remind us we're calculating the Z component of this force. Well, the first part of this is the force on the bottom of that slice pointing upwards. So atmospheric pressure minus rho g Z2 times dA. And we'll just go back to our diagram here. So that's the force pushing in the positive Z direction, in other words, pushing upwards on the bottom of the element of volume. Now, why is it P atmosphere minus Z2? Well, P atmosphere is the pressure of atmosphere up here. And remember, this Z2 is a negative number. So P atmosphere minus rho g Z2 will be the pressure here. It will be a pressure higher than atmosphere because Z2 is a negative number. So whatever that comes out to, that gives the force on the bottom end of this slice pushing up. The other half of this expression gives the force on the top of the slice pushing downwards. And we say that's a negative because the force of the fluid on the top of the slice is pushing downwards, or it's pushing in the negative z direction. Now, other than that, the only difference is that this is based on Z1 instead of Z2. And again, it's minus here because of the direction that we've defined Z. So this is the force on the bottom pushing up. This is the force on the top pushing down. Now realize that atmospheric pressure cancels out of this expression. We have P atmosphere here minus P atmosphere here, and they're both multiplied by dA. So that cancels out, and we can simplify this expression. It just says rho g Z1 minus Z2 times dA. And Z1 minus Z2 is just the height of that slice. And the height of the slice times dA is just dV, our element of volume. So the force in the vertical direction on that element of volume is rho g times dV. Now remember where this rho came from. That rho came from calculating the pressure in the fluid. So that rho is the density of the fluid that this thing is submerged in. It's not the density of the material that the object is made out of. It's the density of the fluid surrounding the object. That's very important to remember. Well, this is dFz, so the only thing left to do here is to add all of those up. In other words, integrate over the entire volume, rho g dV, in order to get the total force in the z direction. So Fz, notice there's no d anymore, that's the total force in the z direction, is rho g triple integral over the entire volume of dV. So realize we are assuming here that rho and g do not vary over the size of that object. We have constant density and constant acceleration due to gravity. Well, the triple integral over the volume of dV is just the volume of the object. So we can just represent this by rho times g times the volume of the object. So this is the buoyancy force. And this is the weight of the fluid that is displaced by the object. So that's the volume of the object multiplied by rho g gives a force, the weight of the fluid displaced by the object. And this is known as Archimedes' principle. So buoyancy force is the weight of the fluid, this should say, it doesn't have to be water, displaced. And that's Archimedes' principle. Now realize that this is true even if the object is partially submerged. So if the density of the object is sufficiently low, then the buoyancy force is high enough to support it on the surface, and it will float at whatever depth is required to make the buoyancy force equal to the weight of the object itself. Now the second topic we want to look at in this video is also related to buoyancy, but it's stability of floating objects. So here we see we have an object that is only partially submerged. So this horizontal line here is the free surface. There should probably be a little triangle indicating that. So we have a liquid of some sort below that line and then just atmosphere above that line. So we have an object here with an arbitrary shape that is floating in whatever this liquid happens to be. So there are two forces acting on that freely floating object. One is its weight, and if we want to represent the weight of this object by a single force like we've done here, then we need to apply that force at a particular location, which is called the center of gravity. So that's what the solid black line is, the center of gravity. So we have our weight applied at the center of gravity. Likewise, the buoyancy force that we've just talked about needs to be applied at a particular point as well. Because remember, this is not actually a single force acting on this object. This is the net effect of the fluid pressure acting everywhere around the surface. So that buoyancy force needs to be applied at the center of pressure. Now, how would we figure out where that center of pressure would be? Well, we would have to calculate the buoyancy force as we've indicated on the previous slides. We would actually also need to calculate the moment that this fluid exerts around the origin of our coordinate system, and then take that moment, divide by the buoyancy force in order to locate this center of pressure. Now that is beyond the scope of this course. We're not going to be finding center of pressure on floating objects like this, but that's how we would do it. We would calculate a moment, divide by the force to figure out where that center of pressure is. But in this illustration, I'm just showing one possible center of pressure to be this location here. Where it actually is will depend on the shape of this object. Now we want to turn to the actual topic of this slide, and that is the stability of this floating object. Well, the way we analyze stability is we take a static situation like this and we disturb it. So realize that for static equilibrium, this buoyancy force and this weight are going to be the same. So this object is going to move up and down until the buoyancy force and the weight are equal. So we have a object here in static equilibrium. That weight equals the buoyancy force. These two vectors are currently collinear, so they don't produce any moment. So the sum of moments is 0 and the sum of forces is 0, static equilibrium. But the question is it stable? So we apply a small disturbance. What we're going to do is reach in and grab this thing and rotate it to the right just a tiny little bit. And so we'll show what that might look like over here. So I've taken this, rotated it a little bit. The center of gravity stays in the same location relative to the object itself. So the center of gravity is still there. The weight is still acting down. It's possible that the center of pressure changes a tiny little bit because there's a different portion or a different shape in contact with the fluid right now. But for illustration purposes, we'll say that center of pressure stays at the same location relative to the object. But the important thing here is that these two forces, because of this rotation, of this disturbance, are no longer collinear. Instead, they produce a moment. So if we take a look at this moment, this is actually a couple because the weight and the buoyancy force are equal. So these two forces produce a couple that is in this direction. It's going to want to rotate this object counterclockwise. So our original disturbance was clockwise, but that produces a moment which is in the opposite direction. So FB and W create a moment which wants to rotate this body in the opposite direction of the disturbance. Realize if our original disturbance had been in the opposite direction, so this original disturbance had been counterclockwise, then the moment produced here would be clockwise. So the key word here is opposite. FB and W create a moment which rotates the body in the opposite direction of the disturbance. So because of that, this is a stable situation. If we have a floating object with this particular configuration of center of gravity and center of pressure, that means that if you reach in and whack this thing or disturb it in some way, and it rotates in either direction, there's going to be a moment produced which tends to move it back to its original position. So this is called a stable situation. Now we want to take a look at a different scenario. So this looks very, very similar, but notice what's happened here. The center of gravity of this particular object is up here. So this weight is being applied at this point. So why would that happen? Well, perhaps there's a different distribution of the mass inside of this object that has moved that center of gravity up to this location. Likewise, notice that the center of pressure is now down here. So why would that happen? Well, this might be a slightly different shape of object, so the center of pressure is now here. The important thing is the relative location of these two. So this buoyancy force is being applied at this point, and the weight is being applied at this point. So currently, the way this is drawn, this thing is still in static equilibrium. There are no moments anywhere because these two forces are collinear, and as long as the weight equals the buoyancy force, then the sum of forces is also 0. So we have static equilibrium here, but the question is, what will happen if this is disturbed? So we're going to do the same thing. We're going to reach in and grab this object, and we're going to rotate it a tiny little bit in the clockwise direction. So if we do that, again, the center of gravity is going to stay in the same position relative to the object. To a first approximation at least, the center of pressure will also stay in the same position. So the important thing is these two forces are now no longer collinear, so they produce a moment. But the problem is, the moment that they produce is in the same direction as the disturbance. So this tiny little disturbance to the right is going to cause a moment which wants to rotate that object even further to the right. So FB and W create a moment which rotates the body in the same direction as the disturbance. So because of that, this is an unstable situation. If we have a floating object which is miraculously in this position here where these forces exactly line up, even the tiniest little disturbance, a little puff of wind or a little ripple on the water, or you touch this a tiny little bit, and again, doesn't matter which direction you disturb it in, it's going to produce a moment that is going to amplify that disturbance or make it move even further in that direction. So this is an unstable situation. So this is just a little discussion of how the shape of an object can have very important consequences to the location of the center of pressure, and likewise the distribution of mass in an object can have very important consequences to the location of the center of gravity. And it's the relative location of those 2 points that determines whether this floating object is stable or unstable. And it all comes down to the moment that is produced when there is a disturbance in the position of that object. So that's the end of our little introduction to buoyancy and stability. In the next and final lecture in the statics module, we're going to look at accelerating systems. So what happens when we have a fluid in a hydrostatic state, but in an accelerating system? So we'll see you in that video.